Yes, let's start. I'm Shunsuke Mori from Linear Technologies. Please call me Kokuyou. It's my online handle. I'm excited to be RubyConf to talk about LLM-based type inference. LLM stands for large language models such as ChatGPT. Can LLM be used for type inference? And can we determine how capable it is? To answer those questions, let's dive into our session. Do LLMs dream of type inference? Now, some of you might be wondering, why use LLMs for type inference in the first place? Let's explore that with a simple example. In this code, there is a bird class and the duck and goose classes that inherit from it. And there's a makeSound method which takes an argument named bird. We call the makeSound method with both a duck object and a goose object. Then, what is the argument type of makeSound method? The traditional method to type inference is algorithmic. I'll focus on data flow analysis here. It analyzes call to the makeSound method and sees that it's called with both duck object and a goose object. Therefore, it infers the argument type is a union of duck and goose. Logically, this makes perfect sense. But would you think the same way? Probably not. You might have thought of it this way. Oh, there is a bird class, and the argument name is bird, so perhaps the argument type is bird object. That's all. This is a heuristic approach using intuition and context rather than strict logic. And it often aligns better with how humans actually write and understand code. So, algorithms are great at logic, but can miss the nuance of human-written code. LLM, such as ChatGPT, offers a different approach. They use heuristic and context much like a human developer. This may bridge the gap between logic and intuition in type inference. Now, can we actually use LLMs for type inference? As an example of using LLM for type inference, I developed RBS Goose and presented it at previous Ruby Kaigi. It infers RBS type definition from Ruby code using LLMs. I named it a goose, sounds like guess, because its behavior is more like an intuitive guess than a logical inference. Note that the bird in the logo is not a goose, but a duck. But this duck quacks like a goose, so it can be used in the logo instead of goose. And you know this is called goose typing. And of course, this is a joke. I digress. Let's get back to talk about type inference. Currently, I have confirmed that RBS Goose can generate RBS type definitions for some small Ruby codes. However, the overall performance of the RBS Goose is unclear, because there is no clear metrics to evaluate the performance of type inference. This will be a problem for future improvements. When I make a change, how do I determine if the performance has improved? So, we need some metrics of type inference performance to see where RBS Goose is now and to make sure that changes are going correctly. Today, I will explain how RBS Goose works with LLMs and evaluate it. Already at this point, RBS Goose shows better results than traditional methods in several cases. Then, I will share the idea of a type inference benchmark that I'm planning to create for more detailed evaluation. For this, I referred to several previous studies. The outline for this session is here. First, we will review the basics of type system and type inference. Next, I will talk about the RBS Goose I developed. Its architecture for type inference using LLM and its current performance evaluation results. After that, I will focus on the evaluation methods used in previous studies as a reference for a more detailed evaluation. Finally, based on these, I will share my idea for TypeEvalRb, a Ruby type inference benchmark. Now, let's start by reviewing the basics of type system and type inference. A type system is a mechanism for classifying the components of a program, such as strings and numbers. Ruby is a dynamic typed language. This means that types are determined only at runtime. For example, 1 plus a raises a type layer at runtime. Furthermore, when this expression is wrapped in if false, the type error is not raised because 1 plus a is never evaluated. To the human eye, the problem with this code is obvious. Is it possible to find this problem on CI or IDE before execution? Static type checking is a mechanism to find such type errors before execution. To do this, we need to know the type of each part in the code without executing it. Unlike C or other languages, Ruby does not use type annotations in its code, so some device is required. One method is to describe the type in RBS language to describe Ruby types. In this case, step can be used for static type checking. Alternatively, solve with RBI or RDL can be used in the same way, but are not covered in this session. As an example, let's look at the case of 1 plus a. We can detect type error if we know the types in 3 parts. 1 is an integer, a is a string, and plus method of integer cannot accept a string. The first two are obvious, and the plus method type for integer is defined in the RBS in the standard library. According to this type definition, the plus method of integer can accept an integer, but not a string. Taken together, we can determine that this code contains a type error without running it. This is how static type checking works. By the way, it is hard to declare for every part in the code. To reduce this workload, type inference is used. Type inference is a mechanism that assists static type checking. It infers the type of code without explicit type annotations. It is primarily used in static type checks to infer types that are obvious from context, such as local variables. For another purpose, it will be used to generate type definitions for Ruby code with no type definitions. TypeProf is a type inference tool that can be used for this purpose. It uses data flow analysis for infer types by tracking the data flow in variable assignments and method calls. Data flow analysis works well in most cases. However, in some tricky cases, the result may differ from human expectation. Consider the bird class example again. In this case, as the argument type of make sound, humans expect the generalized type bird class. However, data flow analysis tracks the types that actually appear in the code and infer union of subtypes duck and goose. This is different from expectation. As another example, static analysis, including data flow analysis, is not good at dynamic definitions. This code uses define method to define print foo and print bar. Static analysis only loads the class structure without running code, so define method is not executed. As a result, the method print foo and print bar are not recognized and inference fails. Since Ruby is many dynamic elements, this will be a major challenge. Now, we will review the type system and type inference, so it is time to talk about type inference using LLMs. Here, I will share about RBS Goose I developed. RBS Goose is a type inference tool using LLMs. It takes Ruby code without type definitions and generates RBS type definitions. This is almost the same input and output as typeprof. However, the mechanism of type inference is very different. Before explaining how RBS Goose works, let us briefly discuss LLM, the large language models. LLM is a language model pre-trained on large datasets. I am sure you all know about ChatGPT. ChatGPT is an LLM trained on conversational data and is adept at answering questions. Let's look at a very simple example. The user enters input text, answer in one line about what Ruby and Python have in common. This input text is called a prompt. ChatGPT will respond to this and generate text explaining the similarities between Ruby and Python. It is very simple, but as natural and powerful as if you were talking about a human being. There are several techniques to make better LLM outputs. Few-shot prompting is a technique in which a prompt is embedded with examples similar to the target problems. Suppose you want to know the color code for blue. Simply ask, what is the color code for blue? The LLM will respond with a summary of various color-coded representations. In the few-shot prompt, include examples instead. Question, red. Answer, sharp FF0000 and question blue. This allows the LLM to understand that the answer format is RGB, yielding the answer sharp 0000FF. Thus, few-shot prompting can be used to define the format of response and suggest inference method to the LLM. Now I have finished explaining LLM, so let's take a look how RBS Goose infers types with LLM. This figure is the architecture of RBS Goose type inference. I will explain components in turn. First, RBS Goose runs RBS prototype command to create a RBS type definition template for target Ruby code. In this template, most types are untyped, meaning that the type is unknown. Next, load the prepared examples. Each example consists of 3 files, a Ruby code, a RBS template, and unexpected RBS type definitions. The expected RBS type definition is almost the same from as the RBS template, with untyped replaced with the concrete types. Then these are combined to construct the prompt. The prompt contains the input and output examples first. Following that, the target Ruby code and the RBS template are provided. LLM follows the given examples and replaces the untyped in the target RBS template with a concrete type. As a result, the output of the LLM looks like this. The RBS type definition is output in Markdown, and RBS Goose parses it and output into a file. This is how the RBS Goose infers types. There are a few key points of the prompt constructions. LLMs are trained with huge amount of data, but contain few definitions of RBS types. For this reason, LLM is not good at generating RBS type definitions from scratch. To address this, I provide an RBS template generated by RBS prototype command. This defines the type inference problem as a fill-in-the-blank problem that replaces untyped in the template with concrete types. As another point, few-shot prompting controls the output format to pass easily. It also provides examples of how special syntax such as attribute reader should be handled in RBS. Now, let's see that type inference can be performed with RBS Goose. How about the examples of bird, duck, and goose? With RBS Goose, the argument type of make sound is inferred to be the bird class. Yes, it works as expected. Interestingly, the Ruby code provided to RBS Goose doesn't include any calls to make sound method. So, there is no explicit relationship in the code between the make sound method and the bird class. Nevertheless, RBS Goose infers the bird class as an argument type for make sound methods. This is probably due to the understanding in the convention of using the same name as the class name for variable names. As another example, let's look at the case of dynamic definitions. In this code, printfoo and printbar are defined using define method. As before, the code calling this method is not provided. Even so, RBS Goose finds the definition of printfoo and printbar and correctly infers the return types. From the result, the LLM correctly understands the concept of dynamic definitions and what methods are defined according to the context. LLM is likely to outperform transitional methods in this area. So, is type inference by LLM perfect? Not quite. This example defines the call method that takes a proc object. TypeProc correctly infers the proc types. On the other hand, RBS Goose makes a mistake in the grammar of the proc types. In these cases, where Ruby or RBS specific syntax is used, the LLM often makes mistakes. Ruby and RBS have various grammar elements, and there are also frameworks such as Rails that are widely used and have unique idioms. To reveal the full performance of type inference using LLM, it is necessary to evaluate on a variety of test cases. However, only a few test cases are being evaluated at this time. Currently, all evaluations are done manually. Not standards for selecting test cases, and the evaluation result is visually checked for difference from the expected types. There are limitations to manual evaluation. This will be a problem for future improvements. When I make a change, how do I determine if the performance has improved? So, we need better methods to evaluate type inference. For reference, let's look at how previous studies have evaluated this. So far, I shared how RBS Goose works and the current evaluation. Next, we will survey how previous studies evaluate the performance of type inference. While there are many previous studies, this session will focus on two. The first is evaluation method of SymTyper, which is type inference tool in Ruby. And the second is TypeEvalRb, which is type inference micro benchmark in Python. Let's start with the first. SimTyper is a Ruby type inference tool that uses a constraint-based approach. This tool is built on a Ruby static type checker called RDL, which is incompatible with the RBS we are currently working on. What is important to us is how they evaluate the performance of type inference. This study compares expected and inferred types for each argument, return values, and variables. Then, for each, the comparison results are classified into 3 categories. When both are exactly the same, it is classified as match. If the base class matches, but the parameters are different, classified as match up to parameter. Finally, if the base class is not matched, it is classified as different. This number of matches can be used as metrics of type inference performance. To evaluate this, we need test data with the expected types. The study used 4 Rails applications with types described in RDL and 4 Ruby libraries with extensive YARD documentations. A graph of the evaluation results is shown here. This graph shows the result of the 4 approaches side by side. The blue area is the number of matches, and the light blue area is the number of matches up to parameter. We can determine that the approaches which has a large blue area is performed better. Such metrics would be useful for quantitative comparisons. I wonder if this evaluation tool could be used for RBS Goose as well, and reproduction data is provided, however, as a VM image. Yes, it's 24 GB. This is not open source and cannot be forked or modified. Furthermore, since it is an RDL-based tool, it could not be used directly in RBS. So, even with Ruby type inference research, I found that the artifacts were not always used directly for our case. Now, let's turn us to previous studies in other languages. TypeEvalRb is a micro-benchmark for type inference in Python. As the name micro-benchmark suggests, this tool covers small test cases categorized by grammatical element and other factors. The evaluation method is similar to SimTyper evaluation. It compares expected and inferred type for each parameters, return values, and variables. However, it covers only exact matches. Now, let's look at the detail of the test cases. Under the test case directory, they are categorized by Python features such as args, assignments, classes, decorators, and so on. Each test case consists of a small Python code and a JSON file which describes the expected types. It's very simple. The results of this benchmark are output in various formats. Here, the tables are shown aggregated by categories. Scalpel in the rightmost column is the name of the inference tool being evaluated. In the built-in categories, the results is 0. This shows that Scalpel is not good at grammars in the built-in category. Thus, micro-benchmark scheme can visualize the strengths and weakness of each inference method by classifying test cases. Now, let's review what we learned from these previous studies. The evaluation in both studies compares the expected and inferred types for each argument, return values, and variables. The number of matches can be used as metrics to evaluate the type inference performance. There are 2 types of test data for evaluation. using real-world data, such as libraries and applications, measures practical performance. On the other hand, using micro-benchmark data based on grammar elements and other factors would allow us to clarify the strengths and weaknesses of each method. Each of these has its own advantages and should be used for different purposes. We have looked at 2 previous studies. Using these previous studies as a guide, I am working on TypeEvalRb, a Ruby type inference benchmark to evaluate the performance of RBS Goose. Still a work in progress, but I will share my ideas. I am planning to build TypeEvalRb with an architecture similar to previous studies. Differently, I am planning to use RBS for both expected and inferred types. The evaluation process is shown in this figure. Prepare Ruby code and expected RBS type definitions as test data, and generate type inferred RBS with RBS Goose. The inferred RBS and expected RBS are compared, and the number of matches is counted as benchmark results. How does we construct the inference type, the inferred RBS type with the expected RBS types? I consider building a comparison tree using RBS environment. The environment loader can be used to load the RBS for a given path. However, the number of class decals is over 300 because stdlib and others are also loaded in this environment. To extract only Goose class, we can use hash access to class decals. The Goose class entry we extracted is here, so deeply nested. This is because class entry has a lot of information. However, only a small part of the information is needed for the comparison tree. The comparison tree construction process has been implemented shown here. I take only the classes defined in the target RBS and create a type node for each instance variables or method parameter and return values to compare. This is a work in progress, and the make sound method of the object class is missing. However, it seems likely that the construction of a comparison tree could be possible. When it is all done, we all have to do is to traverse the comparison tree, count the number of matches, and that is the benchmark result. Next, what should we use for test data? Micro benchmarking and real-world data each have their own advantages. So both should be prepared and used according to the purpose. Like TypeEvalRb, micro benchmark data is categorized by grammatical elements. Using these test data, a detailed evaluation that shows the strengths and weakness of each method should be possible. For real-world data, it would be better to follow SymType's evaluation and use Ruby libraries and Rails application with RBS type definitions. An evaluation using these data should be able to measure practical performance. Since the preparation of micro-benchmark data is work-intensive, so I am exploring the possibility of using the GitHub Copilot workspace, a task automation agent. My little testing has not yielded very good results, but it is worth it to adjust the prompts. Once the tree construction is implemented, I will get to work on this area well. I'm currently working on TypeEvalRb in this direction. It is still in the early stages, but I will gradually work on it as my private project. Finally, let's wrap up. I shared how RBS Goose works and currently evaluation results. This evaluation revealed that LLM provides better inference results than traditional methods in examples such as generalization and dynamic definitions. For more detailed evaluation, we surveyed how previous studies evaluate type inference performance. These evaluations compared expected and inferred types and counted the number of matches for metrics. In addition, both micro-benchmarks and real-world data were seen as test data, and both seems useful. Based on these previous studies, I shared the idea of TypeEvalRb, a type inference benchmark for Ruby and RBS. This development is in the early stages, but hopefully it will reveal the type inference performance of LLMs and can be used for future improvements towards the realization of out-typing. That's all. Thank you for listening.